Hey everybody, before we get into the modular arithmetic proof, let's write down what this statement means in modular arithmetic notation. It says that 23 factorial is congruent to 22. I love this notation. It took me a while to learn it. I think I know it pretty well right now. And it's just so neat to think about divisibility and equality in the same breath. That's what makes it fascinating to me. So that's mod 29 right there. Now, and if you think about divisibility, it's really, there's a lot of things that it shares with equality, like transitivity. If something's equal to it has similar properties. If you look at the reflexivity, transitivity, all that stuff, that make up an equivalence relationship, it's very similar. Divisibility is I think, like a partial order, okay? But in any event, we want to show this. And this statement right here says that 23 factorial minus 22 has a factor of 29. It's divisible by 29. That should read mod, folks. Okay. Now, also just a word, 23 factorial is a huge number. None of us could do this by ourselves. If we tried to do 2 times 3 times 4 times 5, all the way, yes, I left one out on purpose, all the way up to 23, nobody would get it right if you had to do it with pencil and paper, okay? So this is an incredible feat to show that what appears to be a fraction is actually just a natural number, a positive integer. Now, a couple of things before we get started here that turn out to be quite useful. Let's see here, let's do 28 is congruent to -1. 26 congruent to -27 congruent to -2. And here's where the equality part of congruence really comes in handy. 26 congruent to -3. It's all modulo 29. You see, and so on. 25 is congruent to -4. What this means, if we get into a modular arithmetic situation, we can substitute these depending on the nature of the circumstances. 24 is congruent to -5. Okay, and so on, folks. Now, knowing this is useful, but we need kind of a heads up or a jump start on this thing, and that comes in the form of Wilson's theorem. This is just a known result. They prove it in number theory course. It's not particularly difficult. It has to do with multiplicative inverses and the fact that they pair up with each other and they all cancel out, and you end up with this. And you can think of -1 as being p minus 1. Like, in other words, you could think of this as 29 minus 1. So Wilson's theorem gives us this right off the bat. Or starting here, we replace 28 with -1. See right here, folks, 28 is congruent to -1 mod 29, so that's what happened right here. 28 got replaced with -1, okay, and all that was left was 27 factorial, and the minus signs cancel. Now, the minus signs cancel in modular arithmetic precisely because of the fact that if D divides, let's call it -a if you want to, just any D is any divisor, that implies D divides A. In this case, it would be 29, okay? And that's a very simple reason that will make you trust canceling signs in modular arithmetic. It's because divisibility, this is true in divisibility, and this is literally the reason. It's that simple, okay? So you can see right here, 28 got replaced with -1. This -1 canceled, and we got a 1 right here, okay? Now notice right here, 27 is congruent to -2. You see right up here, we wrote that down. Okay, that's exactly what we did right here. So you got -2. You see how we're working our way down. Okay, folks? Now we use these statements all the way through. Okay, and I won't say too much right here. Everything is really based on what we wrote down at the beginning. Now, something that's kind of interesting right here, we have, so we got to this point, 26 factorial is congruent to 14, right? Okay, now you can see right here, you can replace 26 with -3, all right? And so on all the way across. Now, it was useful to replace 14 with negative 15, right? So these two negative values would cancel each other suitably, and we get 25, right? See, that kind of thing happened all the way through here. Now, there's one little sneaky part when you got to this stage right down here. You see how we got to 24 factorial is congruent to 6? Well, 24 is congruent to negative 5, and it's tempting to replace 6 with negative 23. But that doesn't work. You don't get a cancellation. So we added 29 to 6. That's the modulus, and we got 35. So that's how we finished the problem, folks. Kind of interesting. You don't always go. You can go from left and right, in terms of adding multiples of 29. Okay, and so we do get to this point where 23. We got negative 7, which is congruent to 22, and we actually finished off what we were trying to do. 23 factorial is congruent to 22. Okay, and of course it's mod 29. And notice that's what we wrote down at the very beginning. That's equivalent. Did I write it down anywhere? Yeah. 23 factorial is congruent to 22. Modulo 29 is equivalent to the statement. And again, y'all, this isn't as messy as I could have shown a little more work, perhaps. But if you just remember, when you're working with Wilson's theorem, you need to work with statements like this because it creates favorable substitutions. And that really is all that happened all the way down until we got to this point right here where we had to make a decision to replace 6 with 35. Again, 35 minus 6 is 29, right? It would have been tempting to replace it with negative 13, but then if you have a negative 13 here, the minus 5 doesn't cancel nicely, even though it would be a true statement from a modular arithmetic point of view, okay? We get to this stage, and then we move it up to 22, which is what we were interested in because 22 minus negative 7 is 19. So, folks, this does it. We're done. This 23 is factorial is congruent to 22. That means that 23 factorial minus 22, just like what the thumbnail says, over 29 reduces to an integer. In other words, stating that a positive integer in particular is a member of the set of natural numbers. And I just marvel at this stuff. I hate to keep going off, but 10 factorial is already in the millions, right? 23 factorial, literally, challenge any of you, even Terrence Tao, whoever, try to multiply it out. 2 times 23 times 24 times 25. Do it by hand and see if you get what your little calculator returns to you. You won't, okay? You won't. So 23 factorial is a magnificently large number, unpronounceable, and yet just the power of this modular arithmetic gives us the capacity to not worry about the magnitude of these numbers. You're always working with relatively small calculations, even though these numbers you're dealing with are so huge. They're, like we're talking about atoms in the universe, things like that, maybe, who knows. Okay, but anyway, we're done with this. Thank you for viewing.